seeing my face. So a really warm welcome to all of you. Yeah, so as I mentioned to you that I already have some previous experience work in the wind project development in Thailand. So I understand that the challenges developers face when it comes to accurate wind data and wind assessment. So before we jumped into the technical details, so I would like to start uh, with you the short introduction of the Vortex and maybe just a quick recap for those who already know Vortex very well. Um, so I mean, Vortex has been dedicated to support the wind industry for more than 20 years already. We established since 2005. So I mean, with more than 20 years of experience, specialized in wind modeling and high resolution wind data solutions. So our goal has always been to provide reliable, accurate, and innovative tools that help developments make better decisions for the wind farm project worldwide. So it is also very important to mention that we are not consulting firm, which means that we don't do any yield assessment or EYA as you call it, an energy assessment that we don't do. Um, so our focus is only on the on the data delivery, which means that we do not perform, like I said, UIA, but instead we provide the high resolution or high quality wind data that you can use with your preferred tools, such as software like WindPros, OpenWind, and some other like Meteodyne or Wind Simulations, WOPS software, just to carry out your own assessment or analysis. And of course, another key point is that our data is compute on demand. So there is no pre-computed data stored in our interface, which means that every calculation is performed specifically for your request, ensuring accuracies, freshness of the data that are relevant to your project. So let me explain just a little bit of the Vortex downscaling methodologies. So basically, we start by using the reanalyzed data set that are ERA 5, MIRA 2, and CFSR. So basically, these data sets are built from combination of observations collected from like satellite data, the point platform, the airport, weather stations, and more. So each of these sources provide data at a different resolution. So in terms of the spatial resolution, it's ranging from 27 kilometers up to 50 kilometers with the Mara 2, and also the temporal resolution or the interval timestamp. Usually it comes at 1 hour time series. Otherwise, it will be a 6 hour available. So in terms of our downscaling methods, of course, we are using the wolf modelings to downscale. So basically, we input three sources of data, mostly with data 5 by default, because it has the best resolution and it has the best the best temporal resolution and spatial resolution. Yeah, so basically we use data 5 and then we input the topography or SRTM, and then we also input the land use maps or the globe cover. Okay. So these are the input data. So now we have, let's say that if there is a like a request here for a maps or Singapore data, then we create the first domain that's quite big, usually at the regional level. And then we input SRTM, we input the globe covers. So now it's become the 3D modelings. And then we launch the wolf modelings, which is the basically numerical weather predictions. To solve the atmospheric equation and creating a new node point. So from 27 kilometer resolution, then we downscale to 9 by 9. So as you can see, from 9 by 9, then we repeat the process to 3 by 3, 1 by 1 for the macro scales. And then for micro scale, we keep on pushing the area 5 to 300 meters and finally 100 meter solutions. That is the highest resolution we can go. So this multi-step approach ensure that the data you receive is both accurate and tailored to your specific site conditions, moving from global scale information to highly detailed and project win data as a micro siting. Yeah, so that's basically our methodology, just simplified it. So basically, with our Vortex objective is that we are trying to make a new solution that cover and supporting the wind farm development from the beginning. So basically, you can use maps, prospecting new site, trying to pinpoint some new locations, and then you can using our data like single point data to do the P3D studies. So usually where you have no measurement, then you want to cross-check some data before you put a med mask, then you launch some series, and then you cross-check whether it is good enough before you put med mask. And afterward, then you're gonna have a med mask up to 1 year. Then after that, basically you enter into the design phase where you're gonna need a high resolution data, whether it is like area mapping, WRG file, to be input into your software and to run EUA, then we have the solution for that. Um, further on that, we also have some information regarding on the extreme where we can compute very high resolutions, 10-minute time series at the extreme event days, and then you can use it for, foundation design, for fatigue loads, and so and so. And then recently, Vortex also have expand our portfolio into the future forecasting. So basically, we are now only, I mean, we have a spin-off company, Philogo, Nebo, and Climate Scales, and now, as you know, Vortex is basically focused on the past. 40 years of the historical wind data. And now we also expand to the future with short-term forecasting up to 14 days for both wind and solar. And then there's Nebos, where we're trying to do the anomaly forecasting for the next 6 months. And finally, the last one would be for the long term, up to 20 years or 100 years. We're trying to do the climate change projection and trying to see if the the wind speed or the solar irradiance would change over the next 4 or 5 decades, how it would change and how it would impact your renewable asset. So back to Vortex, I'm just going to go briefly with you in terms of the what we offer. So basically at Vortex, we only offer two things. The first one is an area or a maps. It can be a very low resolution map, 1 kilometers, 3 kilometers map for a big area, or it can be a higher resolution map at 100 meters resolution. So this one would be more specific on the site. So if you are looking at very complex site or without no measurement, then this one would be farm and block would be the best idea to start. Otherwise, we have another product that is a point, a single point product where we do the modeling to generate a time series from hourly time series, a 10-minute time series with the tabular information. So any of that we can do. And of course, our product, we are open for the calibrations available. So for whether you have a med mass data or the LiDAR data, we also accept it for the remodelings. And these are the products that you can use the remodeling option. So basically, Gerard will talk through with you in terms of the remodeling and how it works here and there. So just going to briefly mentioning about the Singapore data. So we have basically four kind of Singapore data. So the first one would be the first and the most common use is the series. So we compute a time series at 3 kilometer resolution every 1 hour from the last 10 years, 20 years, 30 years, I mean up to 40 years. Um, this is just the low resolution data, and now we have also the higher resolution data like RES and times, where we compute the time series at a higher resolution like 100 meters or 300 meters. And in terms of the temporal resolution, it's a 10-minute time series for 1 year, one rolling year, or you can choose to have 10 years, 20 years, 30 years of 10-minute time series backwards. So this is these two will be basically focused on this in a couple next slide. And then the next one would be also the just to quickly go into with you with the Vortex Maps product, where you can have just the 1 kilometers map over any area, over the countries or the region of which part of the world you are interested in. Then you can just use it for prospecting. But of course, we have farm and blocks, which is the higher resolution maps, and it comes at the WRG format file. So which means that you can input this data directly into your WinPros or any software that you are using, like OpenWin, and then you can perform the UA um, calculation from that. So yeah, I think that is pretty much a quick recap from my end. So I think I will hand this over to Gerard to speak on the next topic. So Gerard, you can take in and then you can start sharing my screen. Patricia said again, if you have any question, you can feel free to drop a question in the chat, and then we will go through with you afterward. Thank you.
Thank you, Marvin. Now start. Gerard will start his presentation.
Okay, can you hear me? Okay, and see the full screen?
Yes.
Okay, so yeah, hello everyone. My name is Gerard Cabero, and I work as a data scientist at Vortex. And today I will talk about our latest development, latest products, which is Vortex Times. I will focus on the validation of this product, and I will also introduce the calibration, our own internal MCP approach to use on-site measurements to improve the accuracy of this simulation. So yeah, we will cover what I said. First, a quick overview on times and its methodology. I will show the methodological variables that are included in the simulation. I will present some deliverables that are included in the purchase of Vortex Times and show the validation results. Once we have covered the times, I will focus on times remodeling, which is this calibration with a similar scheme, the overview, a calibration example, and the validation. So let's start with times. For those who don't know what's Vortex Times, Marvin has introduced it, but it's a long-term, high-resolution, 10-minute time series, so we can cover up to 30 years, covering the whole vertical profile, so from 10 to 440 meters. And the particularity of this product is that we have enhanced this simulation with our Vortex LES, so it results in an improvement of the subgrid effect and therefore the microscale description. And as I said, there's the possibility to use on-site measurements to calibrate the time series and reduce the uncertainty of the simulation. So as Marvin said, we always use ERA5 analysis since it's the most accurate global analysis. At least it has the best horizontal and temporal resolution. We use the WRF model to downscale it, and basically we run first this baseline WRF simulation, which is the long-term time series that covers the whole period of Vortex times. And in parallel, we run a second WRF LES simulation that explicitly solves the microscale and the local effects. And combining these two simulations with some statistical and machine learning approaches, we can improve the baseline simulation with a well-grounded turbulence description. So this results in Vortex times, which is this microscale, long-term, 10-minute time series. So if we focus on the variables that are included in the simulation, we have the typical variables that we can obtain with the WRF models. So the most important ones would be wind speed, wind direction, and wind standard deviation for the turbulence. We have also some other meteorological variables, such as temperature, density, pressure, humidity, and two variables that are focused on the atmospheric stability description, such as Richardson number and the Molino-Bokov length. And well, this next week's the 3-cyclone gust derived from this WRF LES simulation will also be included in the times. So focusing on all the features that you can have with times, I have first to mention that you can update this time series in a monthly basis. So since we are using ERA 5, we always have the most recent analysis data. So you just have to log into our interface and click the update button. So you will always have free or extra data up to date. And regarding the format, I have shown a screenshot of the text file, but we also have other formats that are compatible with other Win engineering softwares, such as WinPro and OpenWin. And if you need the whole simulation in your computer and use it with or analyze it with Python or other programming languages, we also offer the whole simulation in a NetCDF format. Now we have this new feature or new features, this informative PDF reports. So when the simulation ends, we automatically run 6 different PDFs to analyze some different variables. So we have this general overview PDF that gives you a quick summary of the wind speed, wind direction, or turbulence, just 2 or 3 tables and some graphs. But you can have a deeper understanding on these variables, downloading the wind speed PDF, turbulence intensity, wind direction, also a wave and vertical structure. So, for example, here I have shown you some examples of the plots that you can find inside this PDF. So you can have a look to the daily cycle of the wind speed. Also the seasonal cycle. You can focus on the wave parameters, split it by sectors or by months, by season, and to have a look to the tab file, for example. So now that we have covered this overview about times, I will focus on the validation. So we have used 272 sites worldwide, covering all kinds of topographies. So we have from offshore sites or flat terrain sites to very complex sites in each continent. So here I put the most important metrics, I would say. So we have focused especially in wind speed, obviously, and the turbulence. We have now a well-resolved turbulence thanks to this Vortex LES combination. So basically the mean absolute bias of the mean wind speed is 5.7 in this validation, which is a pretty good number. And the terminal correlation with the measurements is 0.7. Focusing on the TI, we validated the turbulence intensity curve. So the mean absolute bias would be more or less 14%. And the root mean squared error of this 15 to 30 points of the turbulent intensity curve, it would be 1.7%. Now I will introduce the times remodeling, which is this feature included in times to calibrate the time series with on-site measurements. So as I said, it's our internal MCP approach, and it's focused on not only on wind, but also on wind speed standard deviation. So therefore, you can also calibrate the turbulence intensity in times. So as I said, is included in each time runs, and you can request as many calibration as you want to use different periods of your measurements, use different heights. So feel free to request as many as you need. And the delivery time, it's around 1 hour. So here I have a qualitative example of the calibration. So here you have a 5-day time series of the wind speed, and wind speed standard deviation. Sorry, there's a typo here. This should be wind speed, not standard deviation. The second one is the standard deviation. In black, we have the measurements, and in pink, we have the vortex time, so the non-calibrated time series. So we can use, for example, 1 year of measurements that are not included in this period that I'm showing. So this is an out of training period. We can use 1 year of data to train the MCP, and once we perform the prediction for the whole period, we can plot the calibrated times or times remodeling here. And we can see that some events that were not captured at all by times in this first day, on this second day, are much better adjusted after the calibration. And with the wind speed standard deviation, a similar conclusion can be derived, because you can see that the daily cycle of the wind speed standard deviation is much better adjusted. We can also collapse the entire period and go to the aggregated domain instead of time domain, and try to see the benefits of this calibration. So again, for the out of training period, I have collapsed the measurement and the times with no calibration, and I have plotted these three distributions. So wind speed distribution, the wind rose, and the turbulence intensity curve. In this first plot, we can see that although the wind distribution is well captured by vortex times, it shows a slight overestimation of the wind speed. Similar things happen with the wind rose. The overall distribution is well captured, but some sectors are, they differ from the measurements. And then the turbulence intensity curve, although the shape is correctly captured, there's an underestimation here. So again, we perform the calibration for this out of training period, and if we collapse the times remodeling time series and we plot it here, we can see that this slight overestimation on the wind speed has been corrected by time remodeling. Same for the wind rose, and this underestimation of the TI curve has been also adjusted. So, well, one qualitative example is not enough to understand the benefits of this time remodeling. So we have conducted, again, another validation, this time focused on 143 sites, and again, covering all kind of complexity terrain. So 1 year of these measurements have been used for training the algorithm, and the rest is used to assess the performance of this calibration. So again, we have validated vortex times, so the non-calibrated time series. You can see that the numbers are pretty similar to the ones I showed before in the other validation. They differ a little bit because the sites are not exactly the same, but the order of magnitude of these numbers are pretty the same. So we have a 5% of deviation of mean absolute bias in the wind speed in vortex times in the non-calibrated time series, 0.74 in the terminal correlation. So again, when we calibrate the time series for these 140 sites, we can see that the mean absolute bias has been improved, dropping this 5% to 1.6% of mean deviation. And also the time domain has been improved, increasing this temporal correlation from 0.74 to 0.78. This is for the wind speed, but we have also validated the turbulence intensity. So repeating a similar exercise, we start with 10.7% of mean absolute bias in the turbulence intensity curve, and 1.5 of root mean squared error. And again, the effect of this remodeling of this calibration helps us to improve these values significantly. So to sum up, I will just enumerate some key points of this presentation. So I have presented times, which is this long-term high-resolution time series with a well-resolved turbulence, thanks to this combination with Vortex LES. We have shown the validation with a great concordance with measurements, with this 5.7% of wind speed absolute bias, and have presented some deliverables that you have included in the purchase of Vortex Times. So these multiple formats or these informative PDF reports to perform some explorative data analysis for the wind variables. And regarding the Vortex remodeling, remember that you can request as many calibrations as you need for wind and turbulence intensity. And again, the validation has shown good agreement with measurements, dropping this 5% to this 1.5% of wind speed absolute bias. So that would be it from my side. I want to encourage you to take a look to our technical documents that are available in our knowledge center. To take a look to this validation and all the feedback is welcome. Thank you.
Thank you, Gerard. Now Elias will present a case study in the Philippines. Elias, you can start.
Yes. Hello, everyone. I hope you can see my screen now. Today I'm going to talk very briefly about the product that Gerard has introduced, Times, but applied to some recent typhoons that we have seen in Philippines, and see how this product performs. So here is an overview of the typhoon season in the Asia Pacific, and there have been a lot of storms. Some of them have been typhoons, 14 of them, and the strongest event was Ragasa, which was a super typhoon that reached highest speed of 57 meters per second. And this is our data that this data has been retrieved from this data set of Best Track Archive for stewardship. And we will focus on the region of Philippines. If we zoom in this region, there were three main events. Ragasa, which was a Category 5 super typhoon, according to the Saffir-Simpson hurricane wind scale. The other event was a Madmo, which was much milder, was a Category 2 typhoon. And the last one was Fung Wong, which was a Category 4 typhoon. And we will focus on this particular location in mainland Philippines to see how our product performs with these three events. It is expected that for this location, the effect of these two typhoons, that Fung Wong and Madmo, will be, as the track is closer to this location, the magnitude will be higher for these two events. And for Ragasa, it won't be that strong, even though that is the strongest one of these three events. If we zoom a bit more in this region, here is the point that we have studied is Baler, where there is a synoptic weather station. So we can retrieve the data in here, and we also launch time simulation here. These are the tracks of Fung Wong and Madmo. The output of the observations is hourly, and the output of our times is 10 minutes. So we will see that the plots are a bit different between both things, but we can see how it performs. And here are the three main events ordered chronologically in time. So Ragasa was set in the final in the end of September. At the beginning of October, we had this Typhoon Madmo, and in mid-November, it was Fung Wong. And here is the wind speed the wind speed values for these times that we simulated in this location. And you can see that the three main events here in these three bands, we can see that the wind speed is higher in these three events. And now we will focus a bit more on these regions and see how it performs compared with observations. So for Ragasa, here you have two plots. The upper plot is the wind speed. The lower plot is the direction. In orange, you can see the observations. As I said, these are hourly observations. And in blue, you can see the wind speed for vortex times. You can see that it's 10 minutal. It has more texture. And you can see that the agreement on the event is more or less high. You can see that the times is capturing well this event, even though that, as I said before, is far north of this location. You can see that the magnitude of the event is not that strong. This is different for the next event. Here at Madmo, we can actually see the eye passage of this typhoon, and you can see that the vortex times is capturing the event, both magnitude and also timing. You can see this drop in the wind speed. That is exactly when the eye passage, the eye of the storm is passing. So the wind speed drops dramatically, and also the wind direction, change in direction. For the wind direction, you can see that, well, because this is 0 and this is 360, it looks like it's not the same, but it's not actually that different. And you can see also a sudden change in the wind direction for the eye passage of the typhoon. And the last episode is for Fung Wong. Here it is more evident, the eye passage. You can see that there is a huge dip in the wind speed. And also there is a dramatically change in the wind direction. This is so typical from when there is a typhoon passing, that the wind direction change between before the passage and after the passage. You can see that also the observations are doing the same behavior. They start with one direction and then they continue with another. And you can see that also the wind speed agree quite well with between both times and observations. So to sum up, here are some conclusions that times reproduce both the wind evolution of for the timing, for the peak timing and the peak magnitude of the three typhoons. Ragasa was far north, so there is not so a strong signal, but still you can see that the model follows the trend. And for Madmo and Fung Wong, they agree both in intensity and peak winds. And also we can see that the 10-minutal data is essential for capturing wind fluctuation and extreme events. So we can see that times is also very suitable for this kind of events. And that's it. I don't know if you have any questions, or you, Marvin, you can add some information.
Thank you, Elias, and thank you, everyone. Marvin, yeah, if you want to go through the Q&A box and see if there is any question that it hasn't been answered yet, because there was many questions,
Yeah.
which is very nice. And we have already answered some of them, but there are still to be answered.
Yeah, so there are some questions that came in that I think maybe some of them we can answer live right now, and some of the question maybe you can also let me share with you my screen so you can contact with me with your question. Perhaps that would be also helpful. Sorry, just give me a moment. Share. Okay, I'm not sure if you're seeing this screen. So here is my email and contact. So you can drop me an email regarding on any question that you have. So I think we could also look at some of the question from our live chat right now. And I think yeah, okay. Yeah, we have quite a few questions. And some of them already answer in the text, but Patricia, do you have any question that maybe we should bring up and answer on the live right now?
Yeah,
Do you
well,
think?
someone is
How
asking how
is
much does the 10 years wind data cost? That includes the 10-minute data of wind speed, standard deviation, wind direction, etc. I think they are referring to Vortex times. So this is a commercial or a sales question. So maybe you can answer. Gerardo Augusto is asking about the price for 10 years of time.
Yeah, so the pricing of our data usually for 10 year we start at 2,300 euros for 10 years. And then it will be I think around 2,500 euros for 20 years. But I will answer it with you by with the link so you can check our pricing in our website. Where is that? Let's see. Asking for the pricing. Okay, and there's another question that maybe we can. Yeah, of course. There was someone asking if I can have the PDF file. So we will send out the PDF file afterwards. So please let me wait for a couple of days. I will share with you the presentation slide for today, and then you can have a look at the case study in Philippines afterward.
Okay, there's another question. Someone is asking about the difference between blocks and LES, the two products. So maybe Marvin, you can also
Yeah.
answer this
The
one.
different the difference between blocks and area is that with blocks, blocks is the high resolution maps. So you get with blocks you are getting Windows grid maps over an area, and then you can also request it for the time series at 100-meter resolution for every 30 minutes, but it is only limited for only 1 day. Sorry, for 1 year. And for the LES, it's a combination of the wolf modeling coupling with the large edge simulation. So LES is more or less on the single point wind data. So you don't get any information in terms of the wind profile over an area. So instead, you are getting the time series for 1 year rolling that can represent the whole 20 years period of that location, or you can choose to have 365 wind data for a specific year of your choice. So if you choose 2005, then we can compute 2005. Yeah, I mean, I hope that I explained very clear in this one. Yeah.
Yeah. Thank you, Marvin. There are some of the attendees are asking about the where we have carried out the validation, where are these more than 300 points that we have validated. There are I would say they are spread all over the world, but someone is asking about we have points in the northern or eastern Europe or in Australia or in the Philippines. We have to check specifically where these points are because, of course, we have all of them located, and yeah, you can ask us directly through the email, and we will say, well, I know that we already have about 15 in Australia, about 10 points are in India, but we have to check where are all the rest in the Baltics or in Philippines, and we will give you the exact number of all these sites. Okay. There are more questions regarding the extreme or the VREF. What is someone is asking? What is the extreme wind VREF difference between vortex and observation? Maybe this is for Elias.
Yeah, that's a good question, but it's very difficult to answer because BREF is very tricky to measure because it's based on extrapolation of 30 years. So unless you have 30 years of data and you perform a gumball fitting with these observations, and you can get a BREF, it's very difficult to and even this, how do you perform this gumball fitting, is it could be different from one user to another, even though that it's an exact definition, but it can fluctuate a lot if you change one of these 30 points of maximums of year maximums. So it's very difficult to validate the extreme wind BREF between model and observation.
Mhm.
Yeah.
Okay. Yeah, thank you. There are so many questions, and all of them are super interesting, and that we don't have time to answer all of them, but we have all the questions, and we will answer them and send it to you per email. Yeah, we are very sorry that we cannot go through all of them. Maybe a last one. Maybe this is for Gerard, and someone is asking how much of the validation has covered complex terrain in general, and how is the performance? I don't know, Gerard, if you have these numbers or this information right now with you.
I don't have the exact number of the complex terrain sites, but I would say that 30-40% of the sites are categorized as complex or very complex. So
Mhm.
we've tried to have well enough sites for each category. So there are 5 categories: offshore, flat, simple, and complex, very complex. So I would say around 40%.
Mhm. Okay, perfect. Anyway, all this information is in this very detailed report that we have in our resources part of our website and the Knowledge Center, and it is available to download. But we will send anyway all this information together with the presentations and the recording of the webinar to all of you. I don't know if any of you want to add something else, Gerard, Elias, Marvin.
Well, about this last question, just that this validation is split by terrain category in the technical document. So to see the pure performance on complex terrain, you can take a look to the technical document.
Okay, perfect. I will send these documents, the presentation, and the recording to all of you. So yeah, we are here to help and to answer all your questions if you have any afterwards. So I just want to thank you, all of you, for joining us today, for your interest in this topic. And I hope to see you soon in the next webinar.
Yeah, so okay, so let me talk from my perspective also. So I would like to thank you so much for your interest and for joining our webinars today. So we truly appreciate your time and hope this session has been useful and insightful for your work. So I mean, as we wrapped up, so I mean, we would like to wish you a wonderful days, and since the holiday is around the corner. So it's a little bit early, but so I would say Merry Christmas and a Happy New Year from all of us at Vortex. So looking ahead as we are excited to announce that we are planning to having a technical workshop for the first time in Southeast Asia next year. So this would be a great opportunity for for the wind engineering community to network, share study, I mean exchange experience for next year. So we would keep you in touch and update with more details soon. So yeah, I mean finally, I mean if you have any questions and would like to continue the discussion to learn more about our performance in wind modeling, please feel free to reach out to my contact as shown here. And we will be happy to share more with you. So thanks again for being with us today, and we would look forward to seeing you at our future event. Thank you.
Thank you very much.
Thank you. Bye-bye.
Thank you. Bye bye.